Hello class, I'd like you to take a couple minutes to read this problem over and try to understand the problem. I'm going to pause the video, and when you're ready to resume, unpause the video so that we can go on to step 2. Hopefully you've had a chance to read the problem over, and what the company wants us to do is to make a tank that will hold 500 cubic feet inside the tank. So I'm going to just draw a rectangular prism. I'm going to try to abide by what they said that the prism will follow. The base is a square and it's a rectangular prism with an open top. I want you to develop a model and come up with an equation in the second step that would give us what the volume of the tank would be and what the surface area of the tank would be. In addition to that, I'd like you to tell me or talk to the group about which one of these is the constraint and which one of these is the design goal. I'm going to pause the video now and let you guys discuss it. In understanding the problem, they tell us that the tank has got to hold 500 feet cubed. The base must be square, so I've labeled the base to be x. The height of the tank is unknown, and that's what we want to determine also, is what the height and the base dimension should be. This would be our design constraint. The surface area is our design goal. We want to minimize this because the company does not want to waste material. So we have a surface area equation that is a function of two variables, x and h. We need to consolidate those variables. So what I'd like you to do in this step, let's call it step 2a, is I want you to consolidate the variables. So consolidate to one variable. Discuss it as a group, make the consolidation, and turn s into a function of one variable. Okay, well, we're back, and hopefully you identified that since the surface area was a function of two variables, we're going to make a substitution using our constraint, and that's where we're going to let 500 equal x squared times h. That's from the volume constraint, and we solve for h, and h is equal to 500 over x squared. We're going to take that quantity and we're going to plug it in to where the h used to be, and we're going to simplify the expression, so now we just have a single function of surface area with a single variable. The next step would be to graph this function on the graphing calculator. So I'd like you to graph this function on the graphing calculator and see where the critical points would be and what the endpoints would be for this optimization problem. So I graphed the function, and as you can see here, I put the graphing window also settings also on the assignment here, because I wanted to see that the window is very difficult at times with these optimization problems to get just right. So you can see here that our surface area went from 0 to 1,000, and you can see we do in fact get to a minimum value. It's not so easy to set up the window, but when you have numbers of this order, you have to try large numbers to just make sure it fits in your window. So don't give up when you're doing the graphing calculator part. Now let's try to do this more analytically. What I'd like you to do is I'd like you to find the critical points by taking the derivative and setting it to 0 and seeing if in fact we get a minimum value at 10. So do that now with your group, and let's compare answers after the pause. So we take the derivative, and the first part's rather easy. It's the derivative of x squared is 2x. The second part, you have to remember that the derivative of 1 over x as a shortcut is equal to negative 1 over x squared, and that will hustle you through this part of the problem. Now we have to add the fractions. So we choose a common denominator, which is going to be x squared. You adjust the numerator. All this is algebra and pre-calc. We add the terms together. We factor the 2 out. We set the numerator equal to 0, and we get x cubed minus 1,000 equals 0. And for our other critical point, we set the denominator equal to 0. And now we go on and we solve that the only value of x that can be cubed to subtract 1,000 from it to get 0 is x equals 10. And for this, the other critical point is that x equals 0. 0 is not in our domain of our original problem, so we're not really going to be able to test that, but we can test the value at x equals 10. So how would you test to ensure that you found the minimum? So I'd like you to do that test, discuss it with your partners, and let's talk about finding the minimum value, or seeing what the minimum value would be. Hopefully you decided to interval test it, and you put it on a number line, and remember that here's where the derivative is equal to 0. When we plug 9 in, we get, obviously 9 cubed is less than 1,000, so in the numerator we get a negative, in the denominator we get a positive. So over here on this side we have a negative derivative when x is less than 10, and when we plug in a larger value than 10, we'll end up getting a positive over positive, which will tell us that the function went from decreasing to increasing, which results in us knowing or confirming that we found at x equals 10 a local minimum value. The last part of the problem is to solve it and to answer the question they asked us to answer. Original model, and try to find the real dimensions for the tank that has material minimized, and we maintain a 500 foot cubed. So we found the value of x to be 10, so that meant that our base was equal to 10 by 10. So if our tank is going to have a volume of 500 feet cubed, we can just plug that into this equation here and solve for h, and we'd find that when we set the equation of 500 equals x squared times h, we know x is 10, so that forces our height of our tank to be 5, and our dimensions would result in being a tank that has a base of 10 by 10. The tank is 10 feet by 10 feet by 5 feet. I hope this helped, and move on to the next problem if there's time.